you very much. Well, hello everyone. It's a pleasure to be here. I know we are at the end of the conference, so everyone should be very tired, but thank you very much for being here. My name is Paula Martinez. I'm here with Rodrigo Beseiro. We are both co-founders of Marvic, and well, because of that, we get to work on many cool projects regarding artificial intelligence and data. So today we're going to share some of that experience with you. And well, we also wanted to thank the Databricks team. It has been a great conference. So starting a little bit, we're going to talk about generative AI. This is like very trendy right now, actually. With generative AI, we can generate images and text, for example. These are the two main fields where this type of technology is being used. The LLMs, for example, with ChatGPT, it's very popular right now. Stable Diffusion was very popular a few months ago, for example. So it's a technology that is being developed very quickly lately. So today we're going to talk specifically in generative AI for images, and we're going to discuss the two most relevant architectures in this field. The first one is Generative Adversarial Networks, or GANS. This was described a few years ago by Yan Likan. I'm sure many of you know him, as the most interesting idea in the last 10 years in machine learning. Okay, so with these networks, with these neural networks, we can generate very realistic images with a very high quality. So for example, in this image, we are seeing a lot of faces that look very real, but all of them are fake. And we can generate images with different characteristics, like, for example, gender, age, skin tone, and else. The other relevant architecture we're going to discuss is diffusion models and stable diffusion in particular. So this is the state of the art right now in image generation, actually. And for example, diffusion models is the technology behind Midjourney, for example. I'm sure many of you have tried out that. And one key concept here, or a feature of this type of models, is that we can introduce a text prompt or an image to guide the generation. So, for example, we are seeing here a text describing how we want to generate this portrait of a woman, and we can indicate, for example, the style, how's the illumination, and many other characteristics. So all the cool images you are seeing generated on the internet are probably generated using Stable Diffusion, for example. So getting a little bit into the details, into the training of these neural networks and how does this look at inference time, we're going to start with GAN networks. So here we have a high-level architecture, a picture of the architecture. And this was first introduced by Yan Likan in 2014. And this was actually a very innovative idea, because the key concept here is that we are going to have two different neural networks, okay, that are going to compete against each other during training. So we're going to train both of these networks together, competing against each other. So the goal will be to generate an image, okay, out of noise. So the generator, that is the first neural network we are seeing here, the input is noise, and it's going to try to generate an image that looks like the training set. So we're going to have a training set in this case, we have images of digits, for example. And we're also going to have a discriminator, that's another neural network we're going to use. And the job of the discriminator will be to identify fake and real images, to classify them. So the input for the discriminator will be the training set, images for real images, and the fake images generated with another neural network. So with this classification, with the results, we're going to build like a feedback loop that is going to indicate to both neural networks if they're doing a good job, how they can improve. And with this feedback loop, we're going to train both networks together, and they are going to be improving a little bit, each of them, over the training, okay? So this is actually, when we are training this type of networks, you should know that this is a complex and unstable process, actually. And in general, we need, these trainings have high requirements in terms of compute power, for example. And since we are training two networks together, we can encounter some instabilities, as I was just saying. So for example, we are seeing here in this plot, around epoch 100, for example, that suddenly the loss of the generator decreases a lot, right? So in this case, what's going on is that the generator actually found like a weakness of the discriminator and is always fooling the discriminator. So maybe we are training this GAN network and we see, oh, the loss of the generator is very low, the training is done, I'm generating already good images, but that is not necessarily true. We can be in a situation like this one. And if you see a few epochs later, the situation goes back to normal, the discriminator learns how to detect that type of images, and well, everything goes back to normal. So when stopping this type of trainings is kind of subjective, okay? So after we train these networks, we can do inference and generate new images. So at this stage, we are not going to use the discriminator anymore, and we are not going to need the feedback loop also anymore. So this is a simpler stage in that sense. One feature of this, or one characteristic, is that we cannot control the output, actually. We're going to generate images that look similar to the original training set, but at least with this, these original configurations of GAN networks, we can control specific features of the images. So these architectures had a very fast evolution, actually, and since the invention in 2014 of the GAN networks, we have many other developments, and these are some relevant names in that sense. For example, trying to improve the stability of the training. Also, for example, trying to improve the resolution of the images that we can generate. And that's the animation we are seeing on your right. That is how pro-GAN or progressive GANs works. So in that case, we start the training generating very low resolution images. We train the network with that. We allow the network to learn about high-level features, for example, and then we move on and progressively augment the resolution of the images that we generate. Another very relevant name is StyleGAN, of course, from NVIDIA. And these type of networks were the ones that generated the fake images we were seeing. Were very popular because of that. And one key feature of StyleGAN is that it introduces a latent space, okay, of images where they try to disentangle characteristics or features. So as we see in the plot here, we can differentiate, for example, faces of women and faces of men. So in this vectoral space, in this latent space, we can perform actually vectorial operations and move and modify some features of the images that we're going to generate, okay? So this is a very cool feature, actually, and we use this in one of our projects where we needed to generate images of persons, of faces, but modifying a certain characteristic, for example, the age. So in the middle, you are seeing a picture of myself in the latent space, and also some younger and older versions of myself. So this is a very cool feature, actually, because it allows us to control some characteristics. But nevertheless, the efforts that StyleGAN put into controlling this, some weird stuff can happen. For example, if we try to age too much a face, probably glasses will start to appear. And that's mainly because of the dataset we used to train the neural network, because we have a bias towards old people wearing glasses, for example. So that type of things could happen with this type of architectures. So to sum up a little bit about GAN networks, This is a very cool architecture. We can produce very realistic, high quality, with a lot of details images that really look similar to the training dataset. As cons, as I was saying, the training is hard, is complex. And we also, and the features are also somewhat entangled, but some architectures have been some efforts towards reducing that. So now moving to Stable Diffusion and diffusion models. So the idea here, the goal will be to generate a fake image out of noise, just as we were doing with GANS. And for that, we're going to have actually two different processes. The forward diffusion, that's the process of progressively adding noise to an image. So as we see here on your right in the example, we have an image of a flower, and we progressively, in different steps, add noise to that image till we get an image that is pure noise, okay? And the reverse diffusion process is the opposite, actually. It's a process of having an image that is noise, and we progressively subtract, remove noise from that image until we generate something that makes sense to the human eye, that looks like a training set or like a flower like we see here, okay? So we need to train this. We need to train like a denoising model, a model that removes the noise, because we need to have an image of noise and convert that into a real image. So for that, we're going to build a training dataset, and we're going to use the forward diffusion process. So we're going to we're going to add noise gradually, progressively to an image from our training dataset, and we're going to store, to save how much noise we add to that image and the timestamp, I mean, in which step we were. So with that, we're going to generate the dataset as we see here, and that is the dataset we're going to use to train the denoising model. The goal of the denoising model will be to predict how much noise it should remove from the noisy image to generate an image that looks like the original training dataset, okay? As we see here in this image. So in this case, we're going to use a UNet as the denoising model. This is an architecture from 2015. It's called UNet because of the U shape, actually. But we're going to use this data set to train this network so it can know how much noise it needs to remove from an image at a certain step. And after we train this network, we're going to use this denoising model, this UNet, already trained to do inference, to generate images that looks like the original data set. So as we see here, we were going to start with a noisy image, and progressively at each step, we're going to predict with the UNet how much noise we need to remove from the image to generate an image that makes sense, okay? Very good. Now I'm going to leave you with Rodrigo to talk about production pipelines.
So this is great. This sphere is amazing. How does this actually look like on production? And we're in consulting firm, so we get to honor some crazy requests from some of our clients. So I'm going to talk from that experience in that sense. And one of the first cases we had to solve was a client that wanted to show faces from you guys in 10 years, 20 years, under a specific lifestyle effect. So that's you smoking and drinking every day, and show you your face and how that smoking and drinking affected you. So this problem faced many challenges. First of all, data set. It's impossible to build that data set. You have biases, it's really hard to build. If you do get a picture in 10 years, you don't get the 20 years, most likely. And the other stuff, you also need to preserve the identity, because I can show you a face of someone smoking that's older than you, but it needs to be you exactly, that I'm actually showing you the face to be able to generate the impact that we want. And the cost from building all of this can be too high, because otherwise this is not a viable application. And what we did here was basically use the by GANS idea. Paula mentioned this name a few minutes ago. Here we're basically trying to find your space in this vector space, this latent space. Once we have a vector that's close enough to your face, we're going to move that in the plus 10 years direction, plus smoking direction, and we're going to generate that face. The problem comes when you're actually trying to find your face in that space. Because this thing that we intuitively understand that we can do, it's actually a slow iterative process where we take a vector, we generate an image out of that vector, we compare that to the original picture that we're trying to resemble, we measure the difference, we move the vector, generate another image, repeat the process many, many times. So this looks great, but it's too slow. And when we're talking about handling requests from many, many users, this can be a problem. So we started looking into ways of optimizing this, a hack to try to improve this. What we found there was an idea of using pix-to-pix. This is a separate GAN network. GANs were the state of the art at the moment where we actually started this project. Pix-to-pix basically has an input image and an output image. Here in the image I'm actually showing you, you have a segmented image as an input, and you have a close to real world output image on the right, where you actually use this to augment data, generate data sets, and stuff like that. We wanted to use this as input image, your face, output image, your face in 20 years after you smoked every day, okay? And what we did was to utilize a concept that's called knowledge distillation, where you basically have a teacher network and a student network. The teacher, it's usually a larger network, slower in this case, and the student is a smaller, faster network. This is called knowledge distillation because the teacher teaches the student from its output, and with this, combined with what we had done before, we can actually achieve really amazing results. Without losing any quality, we achieved a 20x in inference speed, but we did lose flexibility because in the past, we actually could, once we had that vector of your face, we could move it as much as we wanted on any direction, plus 10 years, plus 20 years, plus 30 years. That was not a problem for us. It was really cheap in inference time. Now we have to train a specific model to be able to learn that plus 10 years, plus 20 years. Despite that, this is really much more efficient than what we did before. It's usually saving a lot of time. We train multiple models, we deploy those multiple models, and depending on the features that you want to add, we just do inference with one or the other. So that's one use case, using GANs. I'm going to talk about another use case. This will be more relatable to many of us in our daily life. So we had a different client that asked us to build a virtual trial application. This basically is e-commerce sites selling any garments, a fashion e-commerce site. And we wanted to show you how the garment would actually look on you before you actually buy that. And this is a huge problem because when you move from the physical experience to the virtual experience, you can't try on clothes. This means that you'll probably get back many of the clothes that you buy because you just don't like them, they don't fit you, stuff like that. And this means a lot of logistics costs that you want to avoid somehow. With this, we try to aim to show you exactly how this would actually look on you. This means body weight as well. This is a problem. And we try to do this with pixel perfect quality. The issue here is that we not only need to preserve the identity of the person, face and body, skin tone, and height, and many other things, and also the garment. And we also need to match the light conditions. Because if I'm actually taking a picture of myself to try to see how the garment would actually look on me, I'm most likely taking a selfie in my home. And that's not the same picture that we'll have from the garment, where we'll most likely have a professional photographer take that picture. Also, we have another problem with the data set. Because the data set, we usually train on pictures from e-commerce sites, and that's usually models. Models tend to be thin. And it's really hard to actually learn that distribution to extrapolate to fatter people, smaller people, taller people, any different bias that we might have on the real world. And there's, of course, this trade-off between the cost of having these servers up and running, inference time, and the quality that we want to achieve. It would be much easier if we could actually do this in lower resolution, but we're aiming high with this. And I can get too much into the details of what we did exactly here. I can share that much of our work was initially based on Bit-on HD. This was state-of-the-art when we started working with this. This was based on GAN networks mainly. And you can see here that we're talking about a really complex computer vision pipeline where we have segmentation models trying to understand the face, the garments, the arms, the legs, and everything. We can also see pose estimation. We also need to be able to mask. So if I'm going to show you a picture of you using a specific shirt, I first need to take out the previous shirt that you're actually wearing. I need to geometrically transform the garment so as to match that pose that you're actually taking the picture in. And then I get to run this through a couple of GAN networks to try to take care of all of the details involved in that pixel-perfect quality that we wanted to achieve. And this was getting great results, amazing results, really state-of-the-art, surpassing state-of-the-art, actually. And then Stable Diffusion came out. And we saw that we could improve that a lot, and we wanted that improvement. So we started trying to understand the best way to use Stable Diffusion in our pipeline. I can tell you that we, first of all, added it as post-processing on many of these things. We're now seeing to replace some of the modules we have already built so as to improve all of this. And I won't get too much into the technical details of that, but I'm going to share some key concepts you need to be aware of if you're going to be working with something similar to this. And the first of all is LORA. LORA has the key advantage, this also applies to LLMs, of significantly reducing the training data that you need to run a fine-tuning on your data. This basically is, we have pre-trained network, and we have a new network that's running parallel. It gets fed with the same input, and you just add the outputs. And with this new network, it's usually way smaller, usually autoencoder-like in a way. So you even have some compression in that sense. And we just train the second network. You get all of the benefits from the pre-trained network, and you get the control from the second network. And this is something that you'll most likely be using when working with this. The other problem, if you're talking about using generative AI in production, there's a huge problem with generative AI. In LLMs, it's called hallucination. So they basically can output anything, and on many occasions, on many critical mission applications, you might even need humans in the loop. We want to avoid that. We want really, really good quality that we can trust that it will never backfire on us. There are some PR cases of really big companies, really state-of-the-art models with those issues. We want to avoid those. So we need to control the outputs. And for that, you usually use classifier-free guidance. This is basically guiding the reverse diffusion process that Paula was talking about so as to be able to have the output that you want. In our use case, I talked about preserving the identity of the garment. If I'm going to be generating an image, I need that image to be exactly the T-shirt I was actually trying to try you on. Classifier-free guidance, basically during the training process, tries to randomly drop out some of the parts of the image. And during inference time, you actually have a weight that you can control how much you like to guide this. And by using that, you can actually find an equilibrium between the trade-off of how much does a network create by itself and create realistic images versus being able to control that. The other key concept that you'll most likely be using is textual inversion. So this is, remember that we're always talking about latent spaces, things that we can actually find, vectors that we can move from one place to the other. This is trying to find to teach to the network a new concept, in this case, the clock. So we give it a text prompt, a photo of S, in this case, a few pictures, the clock, and a few variations of that. And we try to teach the network to that new concept of that clock, so we can actually use that later in some prompts. And how does this actually look like? So we're going to teach it these examples of the statue that we see on the left, and then we're going to ask a photo of Elmo in that same pose. And it's going to be able to create those outputs. In practice, this is used to avoid biases, for example. This is used to augment datasets. In our case, it is used to edit some of the images. And for example, if you give me a picture with you using pants, and I want to try on some shorts on you, I'm going to need to create the legs. Those legs might come with socks. Some of the applications we're actually using with this is trying to remove the socks with textual inversion. And it's all about control when talking about generative AI in production. So ControlNet, that's the other key concept you need to be aware of. ControlNet, in a way, is similar to LORA, where you have a pre-trained network. Here we have a clone of that network that actually gets run in parallel. The input gets fed through both of them. You freeze during training the weights of this pre-trained network, and you initialize the weights of the second network to 0. With that, you can actually get from really early stages in training, really high quality output. You can really reduce the amount of training data that you need, the compute power in order to get really good results, and you gain the control that you want with that second network running in parallel. That during inference time, it's the output of the two networks as well. And summing up some of these things. Stable Diffusion, it's really state of the art. It's impressive. You need to use that if you're going to be working with this. If you can deal with the slow times. It's iterative. That's the process, removing noise step after step. And that's really, really slow. That means a lot of compute power. If you want to use that, be conscious of that part. GAN networks are an excellent alternative. They might not be as good as Stable Diffusion, but they do solve many of the problems that we have. And if you're going to be working with this in production, be conscious as well that this usually involves really complex pipelines. I really haven't seen too much applications where you just have a model, an API, you prompt, you get the response, and that works perfectly. You usually need to implement guardrails, many additional models so as to facilitate some of the processing. In our case, those were classification models, post-detection models, segmentation models. Be conscious of that when designing your architecture and understanding how best to deploy that. And also use LORA, textual inversion, ControlNet, so all of those things so as to be able to gain that control that you most likely need and to be able to reduce those training costs and times. And I talked a lot about this case. I wanted to show you some of the outputs that we're actually getting. It's really hard to appreciate the level of detail, but if you look closely, for example, at the sleeves, you'll be able to see that we're actually generating the skin tone without any biases. That was a huge win for us in many senses. We're also adapting the length of the band so as to match the original length of the band. So there's a lot of work with all of this. Google did release a paper really recently with some state-of-the-art results with a huge, immense data set, and with 4 TPUs on a 32-second inference time, if I'm not mistaken. So we're talking about massive compute power in order to get these results. And some final thoughts on this. Generative AI, it's evolving really, really fast. It's only hyping right now, but this actually started many years ago. I'm not sure if you remember this image from the internet, where we actually saw the evolution from GAN networks in just a time span of 4 years, evolving from what we see on the left to what we see on the right. With this diffusion-based model, Stable Diffusion, we're actually seeing this evolution in a few months. So it's really speeding up, it's really accelerating. We can actually expect impressive results in no time. LLMs, there's a lot of comparisons with LLMs. This tweet where LLMs are having their Stable Diffusion moment. There are many, many points of contact between LLMs and these diffusion models. They both achieve mind-blowing results. They both are really expensive to train, and you need to leverage pre-trained models as much as you can. You'll probably need lots of training data or these hacks so as to reduce that as LORA, for example. and it's really, really hard to control the output. And when we're talking about applications where you don't have a human in the loop, that can be really, really risky. So you need to be really careful about that, and you need to implement those guardrails so as to be safe in that sense. And I just want to round up with a funny story, at least I consider it funny, of a 19-year-old generating a picture with a GAN network that was actually sold for close to $500,000. This is an issue. We need to be really, really careful because there were legal implications to this. Who's the real owner of that picture? Who deserves those $500,000? You need to be careful with the data sets that you use, with the models that you use. You can have some biases, you can have some really big implications because of that.